Consider for a moment what it means to stand before something that can kill you instantly. Not hypothetically, not in theory, but standing there, feeling the charge building in the air, knowing that what you're about to do ended another man's life just months ago. In 1752, Benjamin Franklin made precisely that choice. He stood in a Philadelphia field with a silk kite and a metal key, facing a force that had terrified humanity since our ancestors first huddled in caves. Tonight, he would prove that the fire from heaven could be captured by human hands. Tonight, he would change everything. Before we jump back in, tell us where you're tuning in from, and if these history tales fascinate you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The storm builds on the horizon, and Franklin watches it approach with the focused intensity of a man who understands exactly what he risks. The thunderhead towers 40,000 feet into the atmosphere, a mountain of water vapor and ice crystals, churning with such violence that its interior reaches temperatures 5 times hotter than the surface of the sun. Within that boiling darkness, electrical potential builds to 100 million volts. Franklin knows this. He's measured smaller sparks in his laboratory, calculated their energy, documented their behavior. But this is different. This is nature's fury unleashed, and he means to touch it. The hemp rope in his hands feels ordinary, almost absurd. How can simple fibers connect him to such cosmic power? Yet Franklin has thought this through with characteristic precision. The silk ribbon he holds keeps him insulated from the charge. The metal key dangling from the string will serve as a conductor. The Leyden jar at his side will capture whatever energy the storm delivers, if it delivers anything at all. If the storm doesn't simply kill him where he stands, his son William watches from a nearby shed, tasked with observing but staying safely distant. They've discussed what might happen, the spark that leaps, the tingle of charge, or the alternative neither speaks aloud, the fate that befell Georg Wilhelm Richmann in St. Petersburg just months before, struck down in his laboratory as he attempted to measure lightning's properties. They found Richmann with a red spot on his forehead where the bolt entered, his shoes blown apart by the force. Franklin knows this. He flies the kite anyway. For thousands upon thousands of years, humans have cowered before lightning's fury. We gave it divine names because nothing else made sense. How could mere nature produce such instant terrible power? The ancient Greeks believed Zeus himself hurled these bolts from Mount Olympus, each one a deliberate act of judgment or rage. When the sky split with light and the thunder shook the earth, mortals fell to their knees. This was the anger of gods made manifest. Picture the ancient world for a moment. No understanding of electricity. No concept of charge or current or voltage. You're a farmer in ancient Greece, working your field when the sky darkens. The clouds build and swirl, turning black as night in the middle of the day. Then comes the flash, so bright it burns after images into your vision. The crack of thunder arrives almost simultaneously, meaning the strike was close, terrifyingly close. You smell the ozone in the air, that sharp metallic scent that accompanies lightning. And then you see what it's done. The olive tree that stood for 100 years, that your grandfather's grandfather knew as a sapling, is split down the middle. The trunk is blackened, smoking. The sap inside boiled so rapidly it exploded the wood from within. If that tree had been you, you'd be dead. Just dead. No warning, no defense, no survival. The power that did this came from the sky, from the realm of the gods. What else could you possibly conclude? The Norse saw Thor's hammer Mjolnir splitting the heavens as the god of thunder rode his chariot across storm clouds. In their mythology, Thor protected humanity from giants and monsters, but his weapon was so powerful that even its defensive use shook the foundations of the world. When Vikings heard thunder, they heard their god doing battle on their behalf. When they saw lightning, they saw the flash of his hammer striking true. Egyptian priests recorded in hieroglyphs how a single strike destroyed the lighthouse of Alexandria, one of the 7 wonders of the ancient world. Imagine standing on the shore and watching it happen. The pharaoh's lighthouse stood over 300 feet tall. its beacon visible for 30 miles across the Mediterranean. Ships navigated by its light. Traders knew Alexandria by its towering presence. Then one storm, one bolt, and centuries of engineering reduced to rubble in an instant. The priests wrote that the gods were displeased. What other explanation existed? Chinese astronomers in 200 BCE documented what they called heaven's fire with remarkable precision for their era. They recorded lightning bolts that could melt bronze bells hanging in temples, transforming solid metal into puddles of liquid copper and tin. They described strikes that turned sand into glass, creating twisted formations the Chinese called thunderstones. These observers were sophisticated, careful, scientific in their approach. Yet even they attributed lightning to celestial forces beyond human understanding. In the Americas, separated by oceans from European and Asian thought, cultures independently reached the same conclusion about lightning's divine origin. The Aztecs offered human sacrifices to Tlaloc, the rain and lightning god who held the power to destroy entire villages in seconds. Better to appease such terrible power than face its wrath unprepared. The ceremonies were elaborate, costly, desperate. Because when Tlaloc sent his lightning, whole communities could burn. Thatched roofs ignited instantly. Wooden structures became infernos. People and animals died without warning. From Japan to Africa, from the Norse fjords to the Polynesian islands, every culture that ever looked up at a storm created stories to explain lightning's power. The Yoruba people of West Africa spoke of Shango, god of thunder and lightning, who could strike down the unjust. Aboriginal Australians told of the Lightning Brothers, ancestral beings whose power shaped the land itself. Hindu texts described Indra wielding the Vajra, a thunderbolt weapon that could shatter mountains. And every story across every continent reached the same fundamental conclusion: this force comes from beyond human understanding. From the realm of gods and spirits and powers we dare not challenge. But here is what our ancestors didn't know, what they couldn't know without the tools of science and the courage of men like Franklin. Each year, lightning strikes Earth 8 million times every single day. 8 million bolts scattered across the planet, each one a discharge of electrical energy built up between clouds and ground. They travel at 200,000 miles per hour, crossing miles of sky in milliseconds. The temperature within a lightning bolt reaches 30,000 degrees Celsius, more than 5 times the temperature at the surface of the sun. That's not metaphor, that's not poetry. That's measurement. Consider what 30,000 degrees means. Steel melts at 1,500 degrees. Diamond, the hardest natural substance, vaporizes at 3,800 degrees. The surface of the sun, the massive fusion furnace that sustains all life on Earth, reaches 5,500 degrees. Lightning exceeds all of this by factors that beggar imagination. For a fraction of a second, a lightning bolt creates a channel of superheated plasma, more extreme than almost anything in our solar system. When lightning strikes sand, it can create fulgurites, hollow tubes of glass formed as the bolt's heat instantly melts silicon dioxide and fuses it into crystalline structures. These formations can extend several feet underground, following the path of the electrical discharge as it seeks ground. The resulting glass tubes are fragile, beautiful, and utterly bizarre. They're literal petrified lightning, frozen sculptures of the bolt's trajectory through sand. When it strikes trees, the sap inside vaporizes so rapidly that the trunk explodes from internal pressure. The water in the sap turns to steam in microseconds, expanding with such violence that it tears the tree apart from within. If you find a tree struck by lightning, you'll often see a spiral pattern running down the trunk, where the bolt followed the moisture-rich layer beneath the bark. The tree might survive, scarred but alive, or it might be split in two, destroyed in an instant. When lightning strikes sand, it can create fulgurites, hollow tubes of glass formed as the bolt's heat instantly melts silicon dioxide and fuses it into crystalline structures. These formations can extend several feet underground, following the path of the electrical discharge as it seeks ground. The resulting glass tubes are fragile, beautiful, and utterly bizarre. They're literal petrified lightning, frozen sculptures of the bolt's trajectory through sand. When it strikes trees, the sap inside vaporizes so rapidly that the trunk explodes from internal pressure. The water in the sap turns to steam in microseconds, expanding with such violence that it tears the tree apart from within. If you find a tree struck by lightning, you'll often see a spiral pattern running down the trunk, where the bolt followed the moisture-rich layer beneath the bark. The tree might survive, scarred but alive, or it might be split in two, destroyed in an instant. When lightning strikes humans, the effects vary with terrible unpredictability. It can stop the heart immediately, disrupting the electrical signals that maintain cardiac rhythm. It can scramble the nervous system, causing paralysis or seizures. It can burn distinctive patterns across the skin called Lichtenberg figures, fractal branching that mirrors the lightning's path as it travels across the body seeking ground. These patterns fade within hours or days, temporary tattoos left by electricity itself. Some victims survive with minimal injury. Others die instantly. The difference often comes down to the precise path the current takes through the body. Franklin understands enough to know he's attempting something that should kill him. He's read the accounts. He knows the statistics as well as his century permits. He's corresponded with natural philosophers across Europe who've attempted smaller-scale experiments with laboratory electricity. Some suffered painful shocks, others emerged unharmed. But Richmond's death in St. Petersburg makes one thing abundantly clear. Drawing charge directly from a thunderstorm is potentially fatal. Yet Franklin also understands that the similarity between the sparks in his laboratory and the bolts from the sky cannot be coincidence. For 6 years, since 1746, when he first witnessed electrical demonstrations in Boston, he's been obsessed with this question. Archibald Spencer traveled through the American colonies offering electrical shows, parlor entertainment for the curious and wealthy. People paid admission to see sparks leap between metal rods, to watch hair stand on end from static charge, to feel strange, tingling sensations when current passed through their bodies. Most spectators saw novelty, amusing tricks to discuss at dinner parties. But Franklin, already renowned as a printer, writer, and civic leader, saw something deeper. He watched Spencer's demonstrations with the focused intensity he brought to everything. The sparks attracted to pointed objects, the way metal conducted while glass insulated. The crackle and flash that reminded him of lightning on a tiny scale. Other observers laughed and applauded and went home. Franklin saw patterns that demanded explanation. He returned to Philadelphia and immediately began building his own laboratory. He ordered Leyden jars from Europe, glass vessels coated inside and out with metal foil that could store electrical charge. He constructed metal rods and silk threads, creating apparatus for generating and manipulating static electricity. His home became a workshop where he spent evening after evening conducting experiments, making observations, testing hypotheses. His wife, Deborah, grew accustomed to finding him surrounded by equipment, notebooks filled with diagrams and calculations spread across every surface. Through 1747 and beyond, Franklin systematically explored electricity's properties. He discovered that charge could be transferred from one object to another, but the total amount remained constant. When you charged a Leyden jar positively on one side, the other side became equally negatively charged. Nothing was created or destroyed, only moved. This principle of conservation would prove fundamental to understanding electrical phenomena. He coined term after term, creating vocabulary where none existed. Battery, from multiple Leyden jars connected together like artillery batteries. Charge, for the quantity of electricity held by an object. Conductor and insulator, distinguishing materials that permit or prevent electrical flow. Positive and negative, describing the two types of charge that attract or repel each other. Electrician, for someone who studies electrical phenomena. The words rolled off his pen elegant solutions to the problem of describing something invisible and mysterious. Each experiment brought new insights. Franklin discovered that charge accumulated, most strongly on pointed objects, a finding that would prove crucial for his lightning rod design. He found that electricity could be conducted through surprising materials when conditions were right. Dry hemp insulated, wet hemp conducted. This simple observation would make his kite experiment possible. And always, through all his investigations, the similarity to lightning nagged at him. The crack of a large spark sounded like miniature thunder. The flash illuminated his laboratory like distant lightning. When he drew particularly strong sparks from his equipment, they branched and forked just as lightning did across the sky. The parallel seemed unmistakable. Lightning, he became convinced, is electricity. The same force that makes fur-rubbed amber attract feathers, that makes Leyden jars deliver shocking jolts, that makes his laboratory sparks leap across gaps. The same force, just vastly more powerful. If this is true, if lightning is simply electricity on a grand scale, then it should behave according to the same principles. It should be attracted to metal points. It should conduct through certain materials. It should be capturable, storable, redirectable. The philosophical implications stagger the mind. If lightning is not divine judgment, but natural phenomenon, then the heavens themselves operate according to discoverable laws. The fury of Zeus becomes the flow of charge. Thor's hammer becomes the equalization of electrical potential. The anger of Tlaloc becomes physics. This idea, Franklin knows, will overturn humanity's relationship with the storm itself. For as long as humans have walked the earth, we've feared. Lightning is something beyond our control, beyond our understanding, beyond our reach. Franklin proposes to reach up and touch it, to prove that heaven's fire answers to the same rules as Earth's electricity, to demonstrate that what we feared as divine is actually natural. But first, he must prove it. Words and theories mean nothing without demonstration. The scientific method demands evidence, observation, repeatability. So on this June evening in 1752, as the storm rolls toward Philadelphia, Franklin prepares his kite. The design is elegant in its simplicity, the mark of someone who understands his subject thoroughly. A large kite made of silk, because silk insulates even when damp. A pointed wire extending upward from its peak to attract the charge based on his laboratory findings. Hemp string connecting kite to key, because wet hemp conducts. A silk ribbon from key to hand, keeping Franklin himself insulated from any charge that flows down. And the Leyden jar nearby, ready to capture and store any electricity that descends from the clouds. The wind picks up, carrying the smell of approaching rain. The first drops begin to fall, fat and heavy. Franklin launches the kite, watching it climb into the darkening sky. The hemp string grows taut as the wind catches the silk. Higher and higher the kite rises, its pointed wire extending toward the base of the thunderhead. Franklin holds the silk ribbon, his hand dry inside the shed's doorway, his body insulated from any charge. The key hangs between kite and hand, waiting to serve its purpose. Nothing happens. The rain increases, drumming on the shed's roof. The thunder rumbles closer, each peal louder than the last. Lightning flashes in the distance, brilliant forks that briefly illuminate the landscape, but none near his kite. Franklin waits, patient despite his racing heart. The philosophical debate he's had with colleagues echoes in his mind. Some believe lightning is an electrical phenomenon. Others insist it must be something else, something unique to the heavens. Something that cannot be reduced to laboratory science. Tonight we'll settle the question. If lightning is electricity, it will seek the path he's created. The pointed wire will attract the charge. The wet hemp will conduct it downward. The key will collect it. The Leyden jar will store it. And Franklin will have his proof. If lightning is something else, something divine or otherworldly, his kite will simply fly in the rain, a child's toy tossed into an adult storm, and he'll pack up his equipment and return home to reconsider his hypothesis. The hemp string grows thoroughly soaked. Franklin notices something extraordinary. The fibers are beginning to stand apart, each thread repelling the others as if charged. His pulse quickens. This is exactly what happens to charged objects in his laboratory. They push away from each other. Objects with the same type of charge repel. He leans closer, examining the string's behavior carefully. The individual hemp fibers definitely stand on end, lifting away from each other against gravity's pull. The storm has charged his kite. Cautiously, carefully, with the deliberation of someone who knows he's at the edge of discovery or disaster, Franklin brings his knuckle near the metal key. Before his skin makes contact, before he touches the metal at all, a spark leaps across the gap. A visible spark, crackling and bright, identical in every way to those from his laboratory equipment. His hand tingles from the charge. He pulls away, then approaches again. Another spark jumps, and another. The storm is feeding electricity down his hemp string, charging the key. And the key is discharging to his hand just as a Leyden jar would. The proof is complete, unambiguous, repeatable. Franklin's mind races even as his hand trembles, not from fear but from the sheer magnitude of what he's witnessing. He attaches the Leyden jar to the key and watches as it captures the charge flowing from the storm. The jar fills with electricity from the sky, storing it just as it stores charge from his laboratory generator. This is it, the proof he needed, the demonstration that will convince the world. Lightning and laboratory electricity are one and the same force. The fire from heaven obeys the same laws as the spark from rubbed amber. The gods don't throw lightning. Nature generates it through processes that can be studied, understood, predicted, and controlled. Everything humanity believed about storms and divine judgment and the untouchable power of the heavens has just changed forever. One man with a kite has reached up and caught the fury of Zeus. To understand Franklin's triumph, we must travel back through time, back beyond silk kites and Leyden jars, beyond the age of reason and scientific method, back to when humanity first touched electricity without understanding what it was. 2,600 years before Franklin stood in that Philadelphia field, a Greek philosopher named Thales walked the shores near Miletus, rubbing a piece of amber against his woolen cloak. Amber is fossilized tree resin, golden and translucent, sometimes containing the preserved bodies of ancient insects trapped millions of years ago. The Greeks prized it for jewelry and decoration, but Thales noticed something curious. When he rubbed amber vigorously against fur or wool, it gained a strange property. He placed the rubbed amber near small feathers, and they leaped toward it as if pulled by invisible hands. The feathers clung to the amber's surface, defying their own weight, hanging suspended until he pulled them away. This was magic, or so it seemed to anyone watching. Nothing in the natural world behaved this way. Objects didn't attract other objects from a distance. Stones didn't pull feathers toward them. Wood didn't make cloth leap through the air. Yet amber did exactly this, consistently, repeatably. Thales, being a philosopher who sought natural explanations rather than supernatural ones, recorded the phenomenon. He didn't understand it. He couldn't explain the invisible force that made it work. But he observed it, documented it, and in doing so, took the first step toward understanding electricity. The Greeks called amber electron, from which we derive our modern word electricity. For them, it was simply the name of the substance. They had no concept that they were witnessing fundamental forces of the universe at work. No understanding that rubbing transferred electrons between materials, that the amber gained a negative charge while the cloth gained an equal positive charge, that opposite charges attract with a force proportional to their magnitude and inversely proportional to the square of the distance between them. All of that lay 25 centuries in the future, but Thales had seen something real, something important, something that would eventually unlock one of nature's greatest secrets. The tiny feathers dancing toward amber were responding to exactly the same force that makes lightning strike, that powers our cities, that enables every electronic device we use. Thales couldn't know this, but he saw it happen. He recorded it. And that observation survived the centuries, passed down through the works of other Greek philosophers, waiting for someone to understand its true significance. For 2,000 years, nothing much changed. The Greeks and Romans knew about amber's attractive property. It remained a curiosity, a parlor trick, an interesting demonstration of nature's oddities. No one connected it to lightning. No one imagined it held practical applications. Electricity remained a word without meaning, a phenomenon without theory. Then, in the early 1600s, the pace of discovery accelerated. William Gilbert, physician to Queen Elizabeth I of England, decided to investigate magnetic and electrical phenomena systematically. Unlike the ancient philosophers who speculated from armchairs, Gilbert conducted hundreds of experiments. He tested different materials, documented what attracted and what didn't, measured the strength of attractions, recorded his findings with scientific precision. Gilbert discovered that many substances besides amber could be charged by rubbing. Glass worked, sulfur worked. Even certain crystals could be made to attract small objects when properly prepared. He coined the term electric to describe these materials, extending the Greek word for amber to encompass all substances that shared this property. More importantly, Gilbert distinguished between electric attraction and magnetic attraction, proving they were different phenomena that only seemed similar to casual observation. His masterwork, published in 1600, included descriptions of a device he called the versorium, a primitive electroscope that could detect the presence of electrical charge. It consisted of a small metal needle balanced on a pin, free to rotate. When a charged object approached, the needle turned toward it. Simple, elegant, and effective. For the first time, humans had an instrument that responded to electricity, a tool for detecting the invisible force. But Gilbert's greatest contribution might have been his terrella, a small magnetized sphere meant to represent Earth itself. Through careful experimentation with this model, he proved that Earth generates its own magnetic field, a field that extends far into space. Compass needles don't point north because of some star or distant mountain, but because Earth itself is a giant magnet with field lines extending approximately 60,000 miles into space. This insight revolutionized navigation and demonstrated that invisible forces could span planetary distances. Gilbert's work inspired others. In Germany, Otto von Guericke, mayor of Magdeburg and experimental philosopher, constructed in 1663 what might be called the first electrical generator. He cast a sphere of sulfur the size of a child's head, mounted it on a wooden axle, and arranged it so he could rotate the sphere while pressing his hands against its surface. As the sulfur spun against his palms, it accumulated charge. The effects astonished all who witnessed them. In a darkened room, the spinning sulfur sphere generated sparks visible to the naked eye, crackling blue-white flashes that leaped from the sphere to nearby objects. Small pieces of paper placed 2 feet away suddenly jumped toward the sphere, attracted by its charge. The air around the device took on a peculiar smell, sharp and clean, which we now know as ozone, created by the electrical discharge splitting oxygen molecules. Von Guericke had created artificial lightning, miniature lightning to be sure, but unmistakably similar to the real thing. The sparks, the crackling sound, the attraction of light objects, even the smell, all matched what observers reported from lightning strikes. The parallel should have been obvious, yet most natural philosophers still didn't make the connection. Lightning was a thing of the heavens. Von Guericke's machine was a thing of the laboratory. Surely they couldn't be related. The pace quickened. In 1729, Stephen Gray, an English experimenter with limited means but unlimited curiosity, made a discovery that would prove crucial to understanding electricity. He found that electrical charge could travel through certain materials over surprising distances. Gray suspended hemp thread on silk cords and discovered he could transmit charge through 800 feet of the thread without significant loss. Think about what this meant. Electricity wasn't trapped where it was generated. It could flow. It could move through materials like water flowing through pipes. Gray distinguished between conductors, materials that permitted this flow, and insulators, materials that blocked it. Metals conducted beautifully. Silk insulated perfectly. This distinction opened entirely new possibilities for experimentation and eventual application. Gray demonstrated his discovery with theatrical flair. He suspended a small boy on silk ropes, then charged the boy's body using his electrical apparatus. When spectators brought their hands near the suspended child, sparks leaped from the boy's fingers to their flesh. The child himself felt nothing unpleasant, just a tingling sensation. But the audience gasped at the visible proof that electricity could inhabit a human body without harm. Charles Dufay, a French scientist, extended Gray's work in 1733 with experiments that bordered on the bizarre. Dufay suspended himself from the ceiling using silk ropes, ensuring he was completely insulated from the floor. Then he had assistants charge his body using an electrical machine. As the charge built up, Dufay's hair stood on end. His skin tingled with energy. When he brought his finger near grounded metal, sparks leapt across the gap with audible cracks. But Dufay discovered something more important than showmanship. Through careful experimentation, he found that there were two types of electrical charge, and that like charges repelled, while opposite charges attracted. He called them vitreous and resinous electricity, based on the materials he used to generate them. We now call them positive and negative, but the principle remains the same. Two objects with the same type of charge push away from each other. Two objects with opposite charges pull toward each other. This fundamental rule governs all electrical behavior. Dufay could demonstrate this mathematically. If he charged two pith balls, lightweight spheres made of plant material, with the same type of electricity and suspended them near each other on threads, they pushed apart at angles he could measure. If he charged them with opposite types, they pulled together until they touched. The force between them varied with distance in predictable ways. Electricity was beginning to follow rules, to obey mathematical relationships, to act like a proper natural phenomenon rather than inexplicable magic. Then came the Leyden jar, invented independently by German and Dutch experimenters in 1745, and named for the University of Leiden, where much of the work occurred. This device, seemingly simple, revolutionized electrical experimentation. Take a glass jar, coat the inside with metal foil, coat the outside with metal foil. Add a metal rod that touches the inner foil but insulates from the outer foil. Now you have something remarkable, a device that can store electrical charge for minutes, hours, even days. The Leyden jar worked on principles nobody fully understood at the time. We now know that it's essentially a capacitor, storing charge by separating positive and negative charges on the two layers of foil, with the glass providing insulation between them. The capacity depends on the surface area of the foil, the thickness of the glass, and the dielectric properties of the material. But 18th century experimenters simply knew that it worked, and worked spectacularly. A single Leyden jar, charged with contemporary electrical machines, could deliver a shock strong enough to knock a grown man unconscious. The Dutch physicist Peter van Musschenbroek wrote to a colleague describing his experience with the device. "I would not take a second shock for the Kingdom of France. The sensation was that intense, that overwhelming. Your muscles contracted involuntarily. Your vision flashed white. Your heart raced. For a moment, you were certain you were dying, yet the jar didn't kill. It shocked, certainly. It stunned. But the charge dissipated too quickly to cause permanent harm in most cases. This made Leyden jars perfect for experimentation. They stored enough energy to demonstrate electrical phenomena clearly, but not so much as to pose unacceptable danger. Experimenters could charge them, transport them, discharge them in controlled ways, and observe the results. Demonstrations became increasingly elaborate. In France, the Abbé Nollet arranged 700 monks in a circle, holding hands, and connected the first monk to one terminal of a Leyden jar and the last monk to the other terminal. When he discharged the jar, all 700 monks simultaneously jumped as the current passed through their linked bodies. The experiment proved that electrical charge could flow through a human circuit, that it traveled essentially instantaneously through such conductors, and that it produced identical effects along its entire path. Others discharged large Leyden jars through thin wires and watched the wires glow red-hot, even melt from the energy flowing through them. They ignited gunpowder with electrical sparks. They killed small animals to study the physiological effects of electricity. The Leyden jar became humanity's first practical battery. Centuries before Alessandro Volta would create true batteries based on chemical reactions. By the 1740s, when Franklin began his electrical studies, natural philosophers across Europe had accumulated considerable knowledge about electricity. They could generate it, store it, transmit it, and measure it with increasing precision. They understood that two types of charge existed, and that like charges repelled while opposites attracted. They knew which materials conducted and which insulated. They could create sparks on demand and deliver controlled shocks. What they hadn't done, what nobody had proven, was whether this laboratory electricity bore any relationship to the lightning that split the skies during storms. The sparks looked similar. The crackling sounded alike. But laboratory sparks traveled a few inches, while lightning bolts crossed miles. Laboratory electricity came from rubbed glass or spinning sulfur. Lightning came from clouds and divine sources, or so most people believed. Some philosophers suspected a connection. The British scientist William Wall noted in 1708 that the smell of electrical sparks matched the smell of lightning strikes. Others observed that both phenomena seemed attracted to pointed metal objects. But suspicion isn't proof. Theory isn't demonstration. Someone needed to actually capture lightning, test it, prove it obeyed the same laws as laboratory electricity, that someone was Franklin. But he stood on the shoulders of giants. Every observation Thales made about amber's attraction, every experiment Gilbert conducted with his Torella and Versorium, every spark von Guericke coaxed from spinning sulfur, every foot of thread Stephen Gray used to transmit charge, every shock Charles Dufay delivered to himself, every Leyden jar that surprised an experimenter with its stored power. All of these contributed to the foundation Franklin built upon. The history of electrical science is accumulation. Each investigator added a piece to the puzzle. Each discovery enabled the next. And each generation of experimenters grew bolder, more ambitious, more willing to push boundaries. They transformed electricity from amusing curiosity to scientific phenomenon. They created the tools, the techniques, and the theoretical framework that made Franklin's experiment possible. When Franklin flew his kite into that storm, he carried with him 26 centuries of human investigation. The thread connecting Thales to Gilbert, to von Guericke, to Gray, to Dufay, to Franklin himself, runs unbroken through time. Each man reached a little further into the mystery. Each man illuminated a little more of the darkness. And together, they prepared the ground for the revolution that was coming, because Franklin's kite did more than prove lightning was electricity. It announced that the invisible forces governing our universe could be understood, could be quantified, could be controlled. The age of electricity was about to begin, and it would transform human civilization more profoundly than any revolution before or since. Benjamin Franklin's obsession with electricity began not with lightning, but with entertainment. In 1746, he attended a demonstration in Boston by Archibald Spencer, a traveling lecturer who performed electrical experiments for paying audiences. The show featured all the standard tricks of the era: sparks leaping between metal spheres, A young woman suspended on silk threads, her hair standing on end as she was charged with static electricity. Small objects dancing through the air, attracted to charged rods. The audience applauded, laughed, marveled at the spectacle. Franklin watched with different eyes. He saw beyond the entertainment to the underlying principles. Why did sparks leap specifically between pointed objects? Why did metal conduct so effectively while silk and glass insulated? Why did the crackling sound of large sparks remind him so strongly of distant thunder? Most spectators saw magic. Franklin saw pattern. He saw questions demanding answers. At 40 years old, Franklin was already renowned. His printing business had made him wealthy. His Poor Richard's Almanac had brought him fame throughout the colonies. He'd founded Philadelphia's first lending library, its first fire company, its first hospital. He'd retired from active business to focus on public service and scientific inquiry. Now electricity captured his imagination completely. He returned to Philadelphia and immediately began assembling apparatus. He ordered Leyden jars from England. He constructed his own electrical generator based on von Guericke's design. He filled his home with coils of wire, silk threads, metal rods, and glass insulators. His wife Deborah grew accustomed to finding their house transformed into a laboratory. Every surface covered with equipment, strange smells wafting from his experiments. Franklin approached electricity with systematic intensity. Unlike many natural philosophers who conducted random experiments hoping for interesting results, Franklin formed hypotheses and tested them methodically. He kept detailed notebooks, recording not just successful experiments, but failures, unexpected results, strange observations that didn't fit current theories. This disciplined approach would prove crucial to his discoveries. Through 1747, Franklin conducted hundreds of experiments. He discovered that electrical charge always balanced. When you charged one object positively, something else became equally negatively charged. The total amount remained constant. Nothing was created from nothing. Nothing disappeared into nothing. Charge simply moved from one place to another, redistributed according to rules he was beginning to understand. This principle of conservation represented a breakthrough. It meant electricity wasn't some mystical substance that appeared and vanished arbitrarily. It was a conserved quantity that obeyed mathematical laws. You could track it, measure it, predict where it would go. Franklin created the terms we still use today to describe this. He called excess charge positive and deficit charge negative, terms that elegantly captured the idea of balance and opposition. He coined other terms that became standard. Battery, for multiple Leyden jars connected together, like artillery batteries arranged for battle. Conductor and insulator, for materials that permitted or prevented electrical flow. Charge itself, as the noun describing the quantity of electricity held by an object. Electrician, for someone who studied electrical phenomena. Before Franklin, natural philosophers lacked consistent vocabulary to discuss electricity. After Franklin, everyone used his terms, but terminology was just the beginning. Franklin discovered fundamental principles of how electricity behaved. He found that charge accumulated most strongly on pointed conductors. Place a sharp needle near a charged object, and charge would flow toward the point, draining from the object faster than if you used a blunt conductor. This observation fascinated him. Why should shape matter so much? Why should a pointed rod attract charge more effectively than a sphere? The answer lay in electric fields, though Franklin lacked that concept. Charge concentrates where conductors curve most sharply, and points represent the sharpest possible curves. The electric field strength at a point can be hundreds of times greater than on a flat surface. This makes points both excellent charge collectors and excellent charge emitters. Franklin couldn't explain the mechanism in modern terms, but he observed the effect reliably and documented it thoroughly. He also discovered that you could shield objects from electrical effects using metal cages. Place a charged object inside a closed metal container and no charge appears outside. Place an uncharged object inside and charge it from outside, and the object gains no charge. The metal redistributes its own charge to cancel any external fields. We call this a Faraday cage now, named for Michael Faraday, who would later explain the principle more fully. But Franklin observed and used the phenomenon first. These discoveries accumulated through 18 months of intensive experimentation. Franklin's letters to European natural philosophers spread his findings across the Atlantic. Peter Collinson in London shared Franklin's correspondence with the Royal Society, where they were read with growing interest. Here was a colonial printer with no formal scientific training, making observations that challenged and extended current understanding. The European scientific establishment took notice, but Franklin's mind kept returning to lightning. The similarity to his laboratory sparks seemed too strong to be coincidence. Both produced bright flashes. Both made crackling sounds. Both were attracted to metal. Both could heat thin wires until they glowed. The scale differed enormously, certainly. Laboratory sparks traveled inches, while lightning crossed miles. But fundamentally, weren't they the same phenomenon? In 1750, Franklin published his speculation in a letter to Collinson. He listed the similarities between lightning and electricity in methodical detail. Lightning appears as crooked lines, exactly like long electrical sparks. It strikes preferentially on high points and metal objects, just as electrical charge concentrates on points and flows through conductors. Thunder sounds like the crack of large electrical discharges. Lightning sets fire to flammable materials, just as strong sparks do. The parallels were overwhelming. If lightning was electrical, Franklin reasoned, then it should be possible to draw charge from clouds, just as one drew charge from a Leyden jar. He proposed an experiment. Build a sentry box on a high hill or tower. Mount a vertical iron rod extending 20 or 30 feet into the air. Station an observer in the box with a grounded wire. When thunderclouds passed overhead, the observer should bring the grounded wire near the rod and watch for sparks. Franklin sent this proposal to the Royal Society in London. They published it in 1751, though with skepticism. The idea seemed too bold, too dangerous, too unlikely to work. Drawing fire from the sky. Surely the scale difference made comparison impossible. Laboratory electricity involved tiny forces. Lightning destroyed buildings and killed people. How could they be the same? But in France, Thomas Francois Dalibard read Franklin's proposal with excitement. If the American was right, this would revolutionize natural philosophy. If lightning was electricity, then the most dramatic natural phenomenon known to humanity operated according to discoverable, testable, comprehensible laws. Dalibard had to try the experiment. On May 10, 1752, at Marly-la-Ville near Paris, Dalibard erected a 40-foot iron rod insulated from the ground by a wooden platform. He stationed a retired soldier named Coiffier at the site, with instructions to watch for storms and test the rod when clouds approached. Dalibard himself had to be in Paris that day, but he trusted Coiffier to follow the procedure. The storm arrived suddenly. Coiffier heard thunder rumbling and saw dark clouds approaching. Following his instructions, he took a grounded brass wire and brought it near the base of the iron rod. Before the wire made contact, a spark leaped across the gap with a loud crack. Coiffier jumped back, startled but unhurt. He tried again. Another spark. And another. The rod was drawing electrical charge from the storm clouds, exactly as Franklin predicted. Coiffier immediately sent for the local priest, who verified the phenomenon. More sparks leaped from the rod. The priest sent messengers to Paris. Dalibard rushed to Marly-la-Ville and witnessed the sparks himself. Within days, the experiment was repeated across France. Every trial confirmed Franklin's hypothesis. Lightning was electricity. The most powerful natural force humans had ever witnessed operated according to the same laws as rubbed amber and Leyden jars. News spread across Europe within weeks. Franklin's insight was vindicated. The colonial printer had solved a mystery that had baffled humanity since the dawn of consciousness. But the news came with tragedy. In St. Petersburg, Russia, Georg Wilhelm Richmann attempted to replicate the experiment in his laboratory. Richman was a brilliant physicist, member of the Russian Academy of Sciences, expert in both experimental and theoretical natural philosophy. He constructed his own lightning rod apparatus and waited for storms. On August 6, 1753, during a severe thunderstorm, Richman's assistant urged him to wait for the storm to pass. The lightning was too close, too violent. But Richman insisted. Science required observation at the critical moment. He approached his apparatus to make measurements. A ball of lightning, a rare phenomenon where electrical charge forms a luminous sphere, appeared at the top of his rod. It traveled down the conductor toward where Richman stood. The ball struck him directly in the forehead, passing through his head and into the floor, blowing apart his shoes from the exit wound. He died instantly, the first martyr to electrical science. Richman's death shocked the scientific community, but didn't stop the experiments. If anything, it confirmed the power of what they were studying. This wasn't parlor entertainment anymore. This was genuine natural force, dangerous and real. Richman understood the risks and proceeded anyway. His sacrifice advanced human knowledge. The red spot on his forehead and his destroyed shoes became grim proof of lightning's electrical nature. Franklin didn't learn of the French success until months later. By then, he'd conducted his own proof, the famous kite experiment we've already explored. But Franklin didn't stop with mere demonstration. He immediately saw practical applications. If lightning was electricity, if it sought the path of least resistance, if it concentrated on pointed conductors, then buildings could be protected. The lightning rod emerged from Franklin's laboratory by 1753. The design was elegantly simple. A pointed iron rod extends above the highest point of a building. The rod connects via thick wire to a metal stake driven deep into the ground. When lightning strikes, it hits the rod, which offers an easy, conductive path. The charge flows down the wire and into the earth, dissipating harmlessly. The building remains untouched. Franklin installed the first lightning rod on his own house, then on the Pennsylvania State House, now called Independence Hall. The rods worked perfectly. Buildings protected by them survived storms that destroyed unprotected structures. The evidence was unmistakable, immediate, and practical. Here was science that saved lives and property. Lightning rods spread rapidly across America and Europe. By 1754, hundreds of buildings sported the pointed rods. By 1760, thousands. Ships' masts began sporting them. Church steeples, previously frequent lightning strike victims, gained protection. The simple device saved countless buildings from destruction and prevented thousands of fires. But not everyone welcomed the innovation. Some religious leaders condemned lightning rods as thwarting God's will. Lightning, they argued, represented divine judgment. Protecting yourself from lightning meant rejecting that judgment, placing human cleverness above divine authority. Installing a lightning rod demonstrated dangerous hubris, presuming to control what God had sent. The debate grew heated. In Boston, several churches refused to install lightning rods, despite nearby buildings burning from lightning strikes. They preached that proper faith provided better protection than iron rods. Then lightning struck the steeple of one such church, starting a fire that destroyed the building. Nearby structures with lightning rods stood untouched. The theological argument collapsed under empirical evidence. Franklin watched the controversy with wry amusement. He'd never intended his invention as a challenge to religion. He simply observed that God gave humans minds to understand creation and hands to protect themselves. If God sent storms, God also gave humans the capacity to understand electricity and build lightning rods. Using one's God-given intelligence couldn't constitute defying God's will. The practical value overwhelmed philosophical objections. Lightning rods became standard on important buildings worldwide. Insurance companies began requiring them. Governments mandated them on public structures. Franklin's simple invention, born from his systematic study of electrical phenomena, saved more property in its first decade than any previous innovation in human history. But Franklin's electrical revolution extended beyond lightning rods. His systematic observations, his careful experiments, his clear documentation established a new standard for scientific investigation. He proved that someone without formal training could make fundamental discoveries through disciplined inquiry. He demonstrated that theoretical understanding could lead directly to practical applications. He showed that phenomena considered divine or magical could be explained through natural law. Franklin's work inspired a generation of natural philosophers. Young men across Europe and America began conducting electrical experiments. His terminology became standard. His methods became models. His discovery that lightning was electricity became the foundation for everything that followed. When later, scientists developed electrical theory, created powerful generators, built electrical grids, they stood on the foundation Franklin laid. In 1753, the Royal Society awarded Franklin the Copley Medal, their highest honor, for his electrical discoveries. The colonial printer who never attended university received recognition as one of the world's leading scientists. Harvard, Yale, and William and Mary granted him honorary degrees. The University of St. Andrews made him a doctor, giving him the title Dr. Franklin that he used thereafter. But perhaps Franklin's greatest contribution was philosophical. For millennia, humans had divided phenomena into natural and supernatural categories. Lightning belonged to the supernatural, beyond human understanding, the province of gods and divine forces. Franklin proved otherwise. He demonstrated that the most dramatic natural phenomenon we experience operates according to comprehensible laws. If lightning could be understood, studied, and controlled, what else might yield to systematic inquiry? This question would drive science for the next 2 centuries. If electricity follows natural laws, perhaps chemistry does too. Perhaps biology. Perhaps geology. Perhaps psychology. The universe might operate entirely according to discoverable principles, with no supernatural intervention required. Franklin didn't argue for this conclusion explicitly. He simply provided an existence proof. Lightning bows to natural law. Therefore, perhaps everything does. The man who stood in that Philadelphia field with a silk kite changed more than our understanding of electricity. He changed our relationship with nature itself. Before Franklin, humans saw themselves as victims of incomprehensible forces. After Franklin, we saw ourselves as investigators, capable of understanding and controlling our environment. That shift in perspective, more than any specific discovery, represents Franklin's true revolution. His work on electricity consumed less than a decade of his long life. He conducted his major experiments between 1746 and 1753, just 7 years. Then he moved on to other pursuits: politics, diplomacy, revolution, nation-building. But in those 7 years, he fundamentally altered humanity's trajectory. He proved that observation, experimentation, and reason could unlock nature's deepest secrets. He demonstrated that theoretical knowledge could generate practical benefits. And he showed that a curious mind, systematically applied to nature's puzzles, could achieve what centuries of speculation could not. Franklin proved lightning was electricity. The next question emerged naturally. What else is electrical? The answer came from the most unexpected source, death itself. In 1780, Luigi Galvani worked in his laboratory at the University of Bologna, dissecting frogs for anatomical studies. Italy was experiencing thunderstorms that day, and Galvani had a lightning rod apparatus set up near his workspace, continuing the electrical investigations Franklin had pioneered. As Galvani touched a metal scalpel to the exposed nerve of a dead frog's leg, lightning struck his rod outside. At that precise instant, the frog's leg kicked violently as if alive. Galvani stared at the twitching limb, his mind racing. The frog was dead. Its heart had stopped hours ago, yet electricity had made its muscles contract. He repeated the experiment, this time without lightning, using a charged Leyden jar instead. Same result. Touch the electrical source to the nerve, and dead muscles sprang to life. The implications staggered him. Life itself, he concluded, must be electrical in nature. He called it animal electricity, believing that living creatures generated their own electrical fluid that animated muscles and nerves. Galvani published his findings in 1791, documenting dozens of experiments with frogs, showing that electrical stimulation could reliably cause muscular contraction even in long-dead tissue. The phenomenon was repeatable, measurable, undeniable. His nephew Giovanni Aldini took these experiments to spectacular extremes. If electricity animated dead frogs, what about dead humans? Aldini obtained the bodies of executed criminals and applied electrical current to them in public demonstrations across Europe. When he touched electrodes to facial muscles, the corpses grimaced and smiled. When he stimulated the eyes, they opened and closed. Arms raised, legs kicked. Hours after death, electricity made bodies move as if alive. These demonstrations terrified and fascinated audiences in equal measure. In London, in 1803, Aldini worked on the body of George Forster, executed for murder. He applied electricity to the face, and Forster's jaw quivered. His left eye opened. To observers, it appeared the dead man might revive at any moment. Some spectators fainted. Others rushed from the room. One witness reportedly died of fright shortly after. Aldini wasn't trying to resurrect the dead. He was demonstrating that electricity controlled muscular function, but the theatrical presentations had an unintended effect. They inspired Mary Shelley, who attended similar demonstrations as a young woman. Her novel, Frankenstein, published in 1818, imagined a scientist who used electricity to animate a creature assembled from dead parts. The story became, perhaps, the most famous work of science fiction ever written, all because Galvani touched a scalpel to a frog's nerve during a thunderstorm. But was Galvani correct that life generated its own electricity? Alessandro Volta, professor of physics at the University of Pavia, disputed this interpretation. Through meticulous experiments in the 1790s, Volta proved that electricity came not from the frog's tissues, but from contact between different metals in the presence of moisture. The frog's leg simply detected the current. It didn't create it. Volta's insight led to his greatest invention. In 1800, he stacked zinc and copper discs in alternating layers, separated by cloth soaked in salt water. This voltaic pile generated steady electrical current for hours without stopping. Unlike Leyden jars, which discharged instantly, or friction generators, which required constant effort, Volta's pile produced continuous electricity through chemical reactions between the metals. Each zinc-copper pair generated about 1.1 volts. Stack multiple pairs together and the voltage is added. Volta built piles with dozens of disc pairs, generating tens of volts. For the first time in history, scientists had controllable, sustained electrical current. They could conduct experiments, lasting minutes or hours instead of fractions of a second. This transformed electrical research from studying sparks to studying flows. The voltaic pile was humanity's first true battery, chemical energy converted directly to electrical energy through reactions at the metal interfaces. Zinc dissolved slowly into the salt water, releasing electrons that flowed through an external circuit to the copper. The process continued until the zinc was consumed or the salt water dried out. Simple, elegant, revolutionary. Within months, researchers worldwide were building voltaic piles and exploring what sustained current could do. They discovered electrolysis, using electricity to break water into hydrogen and oxygen gas. They isolated new elements by passing current through molten salts. They created electromagnetic effects impossible with momentary sparks. Volta's battery opened entirely new domains of investigation. In 1820, Hans Christian Ørsted, a Danish physicist, made an accidental discovery that revealed a deep connection between electricity and magnetism. During a lecture demonstration at the University of Copenhagen, he placed a compass needle near a wire carrying current from a voltaic pile. The needle deflected, pointing not north but perpendicular to the wire. Turn off the current and the needle returned to north. Electricity and magnetism weren't separate forces, they were linked. This shocked the scientific world. Magnetism had been studied for centuries. Compasses guided ships. Lodestones attracted iron. But magnetic phenomena seemed completely unrelated to electrical phenomena. Ørsted proved otherwise. Moving electrical charge created magnetic fields that spiraled around the current. Electricity and magnetism were two aspects of a single unified force. Michael Faraday, perhaps the greatest experimental physicist of the 19th century, seized on Ørsted's discovery. Faraday started life as a bookbinder's apprentice in London with almost no formal education, but he attended public lectures on science and became fascinated. He wrote to Humphrey Davy, one of England's leading chemists, asking for work. Davy eventually hired him as a laboratory assistant. Faraday's experimental genius soon surpassed his mentors. Through the 1820s and 30s, he conducted thousands of experiments exploring electricity and magnetism. If electrical current created magnetic fields, could magnetic fields create electrical current? In 1831, he found the answer. Moving a magnet through a coil of copper wire generated current in the wire. No battery needed, just motion. This principle, electromagnetic induction, underlies every electrical generator on Earth today. Move a conductor through a magnetic field and electrons flow. Faraday built the first dynamo, spinning a copper disc between the poles of a magnet. The rotation generated steady electrical current that powered external circuits. Mechanical motion converted directly to electricity. Faraday also built the first electric motor, reversing the process. Sent current through a wire in a magnetic field, and the wire moves. Build the device properly, and rotational motion results. Electricity converted back to mechanical work. These twin inventions, generator and motor, would eventually reshape civilization. But in Faraday's time, they were scientific curiosities, laboratory demonstrations of fundamental principles. Through relentless experimentation, Faraday developed the concept of fields. Electric and magnetic effects didn't require direct contact between objects. Instead, charged objects and magnets created invisible fields filling space. Other objects responded to these fields. Place iron filings around a magnet, and they align along field lines. Bring a charged object near a conductor, and charges redistribute according to field strength. Fields were real, measurable entities with definite mathematical properties. Faraday couldn't express his insights mathematically, lacking formal training in advanced mathematics. But James Clerk Maxwell, a Scottish physicist, translated Faraday's experimental findings into elegant equations in the 1860s. Maxwell's equations showed that electricity and magnetism were not just related, but were two manifestations of a unified electromagnetic field. His mathematics predicted that electromagnetic disturbances should propagate through space as waves traveling at the speed of light. Light itself, Maxwell realized, was an electromagnetic wave. But back in 1847, James Prescott Joule conducted experiments proving that electrical energy and mechanical energy were equivalent. He built apparatus to measure heat generated by current flowing through resistance. The heat energy exactly equaled the electrical energy consumed. He showed that lifting weights with electric motors consumed electrical energy equal to the gravitational potential energy gained. Energy could transform from one form to another, but the total remained constant. Joule's work established the first law of thermodynamics, conservation of energy. Whether energy appeared as motion, heat, electricity, or any other form, it could be precisely measured and accounted for. The universe ran on an exact energy budget. Nothing was created or destroyed, only transformed. These discoveries fundamentally changed electricity from mysterious force to quantified phenomenon. Galvani showed that life itself operated electrically. Volta created controllable current sources. Ørsted revealed electricity and magnetism were unified. Faraday discovered induction and built generators and motors. Joule proved energy conservation applied to electricity, each insight built on previous work, creating an increasingly complete understanding. By mid-century, electricity had laws, units, equations, and practical applications. It could be generated, stored, transmitted, and converted to other energy forms with measurable efficiency. The invisible force that made Thales' amber attract feathers now powered experimental devices and would soon power the world. For thousands of years, human civilization lived by the rhythm of the sun. When darkness fell, people retreated indoors, lighting candles or oil lamps that provided flickering illumination barely sufficient to read by. Night meant danger, limited activity, enforced rest. The invention that would change this forever began with a simple idea. If electricity could create sparks, could it create sustained light? Arc lamps, developed in the early 1800s, proved it could. Pass enough current between two carbon rods, and the gap between them glows with brilliant white light, temperatures reaching 3,000 degrees Celsius. But arc lamps were impractical for most uses. They were blindingly bright, consumed carbon rods rapidly, and required constant adjustment as the rods burned away. They worked for lighthouses and street corners, but not for homes. The solution was the incandescent bulb, a thin wire heated by electrical current until it glowed. The challenge was finding a filament that would glow brightly without burning up. In air, heated wires oxidized and failed within seconds. Remove the air, and they lasted longer, but still not long enough for practical use. Dozens of inventors worked on the problem through the 1870s, each achieving limited success. Thomas Edison attacked the problem with characteristic determination. Starting in 1878, he and his team at Menlo Park, New Jersey, tested thousands of materials for filaments: platinum, nickel, various alloys. Each failed too quickly. Then Edison tried carbonized materials, first paper, then bamboo fibers. These carbon filaments, sealed in evacuated glass bulbs, glowed for hundreds of hours before burning out. By 1879, Edison had a practical incandescent lamp, but a lamp alone wasn't enough. Edison envisioned entire systems: generators to produce electricity, wiring to distribute it, switches to control it, meters to measure consumption, and lamps to use it. He designed every component, from the power station to the light socket. On September 4th, 1882, Edison's Pearl Street station opened in Lower Manhattan, the world's first commercial power plant. 6 dynamos, each weighing 30 tons, turned day and night. They generated 100 kilowatts total, enough to light 800 incandescent bulbs within 1 square mile. Customers paid for electricity the way they paid for gas, by measured consumption. The system worked flawlessly. Within months, hundreds of buildings had electrical service. Within a year, thousands of bulbs glowed across Lower Manhattan, but Edison's direct current system had limitations. DC voltage couldn't be easily transformed to higher or lower values. This meant transmission over long distances resulted in enormous power losses. Edison's generators needed to be within a mile of customers. To electrify a city required power plants every few blocks. An expensive and impractical approach for widespread deployment. Enter Nikola Tesla, a Serbian engineer who arrived in New York in 1884 with 4 cents in his pocket and revolutionary ideas about alternating current. Unlike DC, which flows steadily in one direction, AC reverses direction dozens of times per second. This seems disadvantageous until you realize that transformers can easily step AC voltage up or down. Generate at moderate voltage, step up to high voltage for efficient transmission over long distances, then step down to safe voltage for use. Simple transformers accomplish this with 98% efficiency. Edison dismissed AC as dangerous. High voltages could kill, and AC systems use thousands of volts for transmission. To prove his point, Edison staged public demonstrations where he electrocuted animals using AC current. Dogs, cats, even an elephant named Topsy died in Edison's publicity campaign against Tesla's system. He coined the term "getting Westinghoused" as slang for being electrocuted, attacking George Westinghouse, who had bought rights to Tesla's patents and was promoting AC power. Tesla responded with demonstrations of his own. He sat calmly in a chair while millions of volts from his Tesla coil created spectacular electrical displays around his body, lightning bolts arcing in every direction. The voltage was high, but the frequency was so rapid that current couldn't penetrate his body deeply enough to cause harm. He proved that AC, properly handled, was safe. The War of Currents reached its climax with the contract to illuminate the 1893 World's Columbian Exposition in Chicago. Edison bid to provide DC power. Westinghouse, using Tesla's AC system, underbid him significantly and won the contract. The fair opened with 200,000 incandescent bulbs, transforming night into day, consuming 3 times more electricity than the entire city of Chicago normally used. 90,000 horsepower of generators drove the system flawlessly for 6 months. The public saw the future. AC had won. Within a decade, AC systems were replacing DC installations across America and Europe. Edison's Pearl Street station, once revolutionary, became obsolete. Tesla's polyphase AC motors and generators became the standard worldwide. The next great demonstration came at Niagara Falls. In 1895, the first large-scale hydroelectric plant began operation, using the falling water to spin massive generators. These produced 11,000 volts, transmitted 20 miles to Buffalo, New York. For the first time, substantial power traveled long distances economically. The age of the electrical grid had begun. Power lines spread like neural networks across continents. By 1900, electricity reached major cities throughout the industrialized world. By 1920, 40 million Americans had electrical service. Factories that once ran on steam power converted to electric motors. Streetcars replaced horse-drawn carriages. Electric elevators made tall buildings practical. Refrigerators preserved food. Electric pumps brought running water to homes. Washing machines and vacuum cleaners transformed domestic labor. The transformation happened faster than anyone predicted. In 1890, electricity was a novelty. By 1920, it was indispensable. Cities blazed with light at night. Factories ran 24 hours a day. Communication became instant with telegraph and telephone. Entertainment arrived via radio. The rhythm of human life, governed by sunrise and sunset for all of history, suddenly became negotiable. Work continued after dark. Activities once impossible at night became routine. The electrical grid itself became Earth's largest machine, a technical marvel spanning continents. Generators thousands of miles apart spin in perfect synchronization, maintaining exactly 60 cycles per second in North America, 50 cycles per second in Europe. Voltage and phase must match precisely for the system to work. Enormous transformers step voltage up and down. Circuit breakers protect against faults. Load balancing ensures supply meets demand every moment. Today's grid delivers power at efficiencies exceeding 95%. Electricity travels from power plant to outlet in less than 1/60th of a second. When you flip a switch, generators potentially hundreds of miles away respond within milliseconds, increasing output to match your demand. The system operates continuously, invisibly, reliably, supporting every aspect of modern civilization. Consider what this means. Franklin captured lightning with a kite. Edison lit 800 bulbs in 1 square mile. A century later, billions of devices consume electricity continuously. Every light, every computer, every phone charger, every appliance draws power from the grid. Modern civilization would collapse without electricity within hours. Hospitals, water systems, communication networks, food distribution, everything depends on steady electrical power. The revolution continues accelerating. Solar panels convert sunlight directly to electricity. Wind turbines generate power from moving air. Nuclear reactors split atoms to boil water and spin generators. Battery systems store energy for when the sun isn't shining and wind isn't blowing. The grid grows smarter, balancing supply and demand in real time, routing power along optimal paths, responding to failures automatically. From Franklin's spark to cities ablaze with light took just a century and a half. From darkness to illumination, from mystery to mastery, from cowering before lightning to channeling billions of watts through copper wires to power civilization itself. The transformation stands as humanity's greatest technical achievement. Modern civilization channels 2 trillion watts continuously. To grasp this scale, imagine 20 billion lightning bolts striking simultaneously, their combined power flowing through cables that circle Earth 40 times over. Every second of every day, this invisible river of energy powers our world. Yet even this staggering quantity represents just the beginning of what electricity can do. Quantum mechanics reveals electricity's true nature, and it's far stranger than Franklin could have imagined. Electricity isn't a fluid flowing through wires. It's streams of electrons, fundamental particles, each carrying negative 1.6 times 10 to the minus 19th coulombs of charge. These particles are both matter and wave, existing in probability clouds until observed, behaving according to rules that defy common sense. When electrons flow through copper wire, they don't race along like water through pipes. They drift slowly, perhaps millimeters per second, while the electric field propagates at nearly the speed of light. Think of it like a tube filled with marbles. Push one marble in at one end, and another immediately pops out the other end, even though no individual marble traveled the full length quickly. The signal moves fast. The charge carriers move slowly. In semiconductors, electrons behave even more bizarrely. Silicon crystals doped with impurities create regions where electrons flow easily, and regions where their absence, called holes, acts like positive charges flowing the opposite direction. Modern transistors exploit these properties, switching billions of times per second through channels measuring just 2 nanometers, approaching the fundamental limit where quantum uncertainty makes smaller circuits impossible. Computer processors pack billions of transistors into chips the size of postage stamps. Each transistor switches on and off 5 billion times per second, controlled by voltages of less than 1 volt. The precision required staggers the mind. 2 nanometer features mean you could fit 4,000 transistor gates across the width of a human hair. Manufacturing at this scale requires atomic-level control, achieved through techniques like extreme ultraviolet lithography, using light with wavelengths of 13.5 nanometers. But some materials eliminate electrical resistance entirely. Superconductors, cooled to negative 270 degrees Celsius, just 3 degrees above absolute zero, conduct electricity with absolutely zero resistance. Current flows through them forever without loss. A superconducting loop, once charged, maintains its current for years without any power input. The electrons pair up in quantum mechanical states called Cooper pairs, flowing through the crystalline lattice without scattering off atoms. The Large Hadron Collider uses superconducting magnets generating fields of 8.3 Tesla, 100,000 times stronger than Earth's magnetic field. These magnets bend beams of protons accelerated to 99.9999% the speed of light. So fast that time dilation makes their effective lifetime 11 times longer than if they were stationary. The entire system operates at 1.9 Kelvin, colder than outer space, maintained by liquid helium. Wireless charging, once science fiction, now transmits power through magnetic resonance. A coil in the charging pad generates an oscillating magnetic field. A coil in your phone picks up that field and converts it back to electricity. The technology fulfills Tesla's century-old dream of electricity without wires, though at much shorter ranges than he envisioned. Modern systems achieve 85% efficiency, transmitting power across a few centimeters. Solar panels perform an even more remarkable trick, converting photons directly to electrical current. When light strikes a semiconductor junction, photons knock electrons loose from atoms. The junction's electric field separates these charge carriers before they recombine, creating current flow. Modern panels achieve 22% efficiency, converting more than 1/5 of incoming sunlight into electricity. Improving efficiency beyond 30% faces fundamental thermodynamic limits. The human brain operates on just 20 watts, less power than a typical light bulb, yet its 86 billion neurons fire electrical signals, creating consciousness itself. Each neuron maintains a voltage difference of 70 millivolts across its membrane through ion pumps that consume adenosine triphosphate. When stimulated, sodium channels open and the voltage spikes to positive 30 millivolts in 1 millisecond, propagating as an action potential along the axon at speeds up to 120 meters per second. These electrochemical signals, traveling through trillions of synapses, somehow generate thought, memory, emotion, and awareness. We can measure the voltages, we can trace the pathways, we can map the connections. But how electrical patterns become subjective experience remains one of science's deepest mysteries. The same force Franklin captured from clouds somehow gives rise to everything we are. Electric aircraft using distributed propulsion place multiple small motors along wings instead of a few large engines. This achieves 90% efficiency, converting battery power to thrust, compared to jet engines' 35% efficiency, converting fuel to thrust. The disadvantage is energy density. Jet fuel stores 40 times more energy per kilogram than the best lithium batteries. But efficiency matters. Electric vertical takeoff and landing aircraft, eVTOLs, are already flying, promising to revolutionize urban transportation within decades. Plasma rockets accelerate ions to 50,000 meters per second using electric fields 10 times faster than chemical rockets. Though their thrust is measured in newtons rather than tons, they can run continuously for months or years, eventually achieving velocities impossible for chemical propulsion. The Dawn spacecraft used ion drives to visit 2 asteroids, changing velocity by 11 kilometers per second, far more than any chemical rocket could achieve with similar fuel mass. Fusion reactors attempt to recreate stellar cores on Earth. They confine plasma at 100 million degrees Celsius using magnetic fields, temperatures where hydrogen nuclei overcome electromagnetic repulsion and fuse into helium, releasing enormous energy. The challenge is containment. At such temperatures, plasma would vaporize any physical container instantly. Only magnetic fields shaped into complex topologies can hold the plasma away from walls. ITER, the International Thermonuclear Experimental Reactor under construction in France, will use superconducting magnets consuming 300 megawatts to confine plasma generating 500 megawatts of fusion power. If successful, it will demonstrate net energy gain from fusion for the first time, proving that humanity can harness the same process that powers stars. Commercial fusion power might arrive within decades, providing unlimited clean energy from hydrogen extracted from seawater, lightning. Franklin's starting point carries about 1 billion joules per strike. Modern civilization uses 20 trillion joules per second, 20,000 times more than all lightning striking Earth combined. We've exceeded nature's fury through our mastery of the electrons Franklin first captured. Yet we're still learning. Quantum computers operate with electrons in superposition, existing in multiple states simultaneously, performing calculations impossible for classical computers. Room temperature superconductors, if achieved, would revolutionize power transmission and energy storage. The electromagnetic spectrum extends from radio waves kilometers long to gamma rays smaller than atoms. We've learned to generate, detect, and use radiation across this entire range. Radio carries information through the air. Microwaves cook food and transmit data. Infrared provides night vision. Visible light illuminates our world. Ultraviolet sterilizes. X-rays reveal hidden structures. Gamma rays treat cancer. All are electromagnetic waves, all governed by Maxwell's equations, all fundamentally electrical phenomena. From rubbing amber to quantum computers represents humanity's journey, from ignorance to understanding. We've progressed from wondering why feathers stick to amber to generating and controlling electrical power measured in trillions of watts, to manipulating individual electrons in quantum devices. The path leads from Thales on the beach to Franklin in the storm, to engineers designing circuits atom by atom. Yet electricity remains fundamentally mysterious. We harness it, channel it, depend upon it. But we cannot fully explain why negative and positive charges exist, why they attract and repel, why the electromagnetic force has the precise strength it does. Quantum field theory describes electricity as excitations in fields permeating all space, with virtual photons appearing and vanishing in 10 to the minus 43 seconds. But deeper questions remain as we reach toward fusion power and quantum computation, as we consider harvesting energy from black holes' rotating magnetic fields, or building space elevators using superconducting cables. We follow paths illuminated by Franklin's kite. Every circuit, every device, every application traces back to that moment when human hands first captured lightning's fire and proved the heavens follow natural law. Franklin's kite experiment echoes through time. That spark, jumping from key to knuckle on a June evening in 1752, fundamentally changed humanity's relationship with nature. We transformed from victims of lightning to masters of electrons. But the story doesn't end with human achievement. It begins there. Every second, 100 lightning bolts strike Earth. They've been striking at roughly this rate for billions of years, long before humans existed to fear them or understand them. This planetary electric circuit connects ground to ionosphere through 2,000 simultaneous thunderstorms, maintaining a potential difference of 400,000 volts between Earth's surface and the edge of space 60 miles up. Think of Earth as a giant spherical capacitor. The surface is negatively charged. The ionosphere is positively charged. Without thunderstorms constantly replenishing this charge separation, the circuit would discharge in minutes. But storms act as generators, using the mechanical energy of rising and falling air to separate positive and negative charges, pumping current upward and maintaining the global electric field. This planetary heartbeat influenced evolution itself. Life emerged in an electrically active environment. The first self-replicating molecules formed in seas beneath skies that flashed with lightning. Some researchers propose that lightning strikes provided the energy needed to forge complex organic compounds from simpler molecules. The spark that creates life might have been literal. Certainly, life learned to use electricity early. Ion channels appeared in cellular membranes 2 billion years ago, allowing cells to maintain voltage differences across their boundaries and to signal using electrical pulses. These same mechanisms power your neurons today. The same fundamental process that let ancient bacteria respond to their environment now enables you to read these words, to remember, to think. The electrical principles Franklin discovered operate in every living cell. Sodium and potassium pumps maintain voltage gradients. Action potentials propagate along nerve fibers. Muscles contract when electrical signals trigger calcium release. Your heart beats because specialized cells generate rhythmic electrical pulses. Life and electricity intertwine at the most fundamental level. Today, 7.8 billion humans consume 18 terawatts continuously. 18 trillion watts of electrical power flowing through grids spanning continents. From space, Earth's night side glows with light from cities, a web of illumination marking human presence. Our electromagnetic signature, radio and television broadcasts, radar pulses, Wi-Fi signals, has propagated outward at light speed for a century. Any civilization within 100 light-years could detect us by our electrical emissions alone. We've reshaped Earth's electromagnetic environment. The global electric circuit still functions, still maintains 400,000 volts between surface and ionosphere, but now it's modified by millions of miles of power lines, billions of electronic devices, countless radio transmitters. We've added a human-made electromagnetic layer to the planet's natural systems, yet electricity remains mysterious. We've mastered its practical applications without fully understanding its fundamental nature. Why do negative and positive charges exist? Why do they attract and repel? Why does the electromagnetic force have precisely the strength it does, neither stronger nor weaker? Change the electromagnetic force constant by just a few percent and atoms couldn't form. Chemistry couldn't exist. Life would be impossible. Quantum field theory provides our deepest understanding. The electromagnetic field permeates all space, even vacuum. What we call electrons and photons are excitations in this field, waves in an invisible ocean. When electrons interact, they exchange virtual photons, particles that appear and vanish in 10 to the minus 43 seconds, too briefly to violate conservation of energy. These ghostly messengers carry the electromagnetic force, but this explanation simply pushes the mystery deeper. Why does the electromagnetic field exist? Why does it have the properties it does? Physics can describe how electricity works with exquisite precision. We can calculate electromagnetic interactions to 12 decimal places. But why remains unanswered. Franklin's legacy lives in every application of electrical science. Bioelectricity research explores using electrical stimulation to heal spinal injuries and restore nerve function. Paralyzed patients regain movement through implanted electrodes that bypass damaged nerves. Blind people see through prosthetic retinas that convert images to electrical signals the brain can interpret. Deaf children hear through cochlear implants that stimulate auditory nerves directly. Transcranial magnetic stimulation treats depression by using magnetic fields to induce electrical currents in specific brain regions. Deep brain stimulation relieves Parkinson's symptoms through electrodes delivering carefully timed pulses. We're learning to read neural signals and translate them into commands for prosthetic limbs, giving amputees natural control through thought alone. The boundary between biology and technology blurs as we master bioelectricity. Quantum computers calculate using electrons in superposition, existing in multiple states simultaneously until measured. A classical bit stores either 0 or 1. A quantum bit, a qubit, stores both until observation collapses it to a definite state. Systems with multiple qubits explore all possible combinations simultaneously, solving certain problems exponentially faster than classical computers. Today's quantum computers have dozens of qubits. Within decades, they might have millions, sufficient to break current encryption, simulate molecular interactions perfectly, optimize complex systems beyond classical capability. They'll operate at temperatures near absolute zero, using superconducting circuits or trapped ions, manipulating individual quantum states with precision Franklin couldn't imagine. As we reach toward the stars, electricity propels us and drives using electric fields to accelerate xenon ions power spacecraft to asteroids and beyond. Solar panels convert sunlight to electricity that runs life support, communications, scientific instruments. Future missions might use nuclear reactors generating hundreds of kilowatts for electric propulsion, enabling trips to the outer solar system in years rather than decades. Some researchers propose harvesting energy from rotating black holes. The Penrose process extracts rotational energy through electromagnetic interactions with the ergosphere, the region just outside the event horizon where space-time itself is dragged around. A sufficiently advanced civilization might tap black holes as power sources, extracting energy from the universe's ultimate gravitational wells, closer to home. Space elevators might one day use superconducting cables to connect Earth's surface to orbit. Electromagnetic climbers would ascend these cables powered by ground-based lasers or beamed microwave energy, lifting payloads to space for a tiny fraction of rocket costs. The cables would carry not just climbers, but electrical power, linking orbital solar arrays to ground stations, potentially transmitting terawatts from space-based collectors to Earth. Lightning still strikes Earth 8 million times daily. Thunderstorms still pump current through the global circuit. The electrical dance that began billions of years ago continues unchanged by human understanding. We've learned to channel and control electrons, but we haven't altered electricity's fundamental nature. We've joined the dance, not replaced it. Stand outside during a thunderstorm and feel the hair on your arms rise as electric fields build. That sensation connects you to every human who ever feared lightning, to Franklin flying his kite, to Thales rubbing amber, to the first organism that used ion channels billions of years ago. The same force flows through all of us. The universe is electrical at its core. Atoms hold together through electromagnetic forces between nuclei and electrons. Chemical bonds form through electromagnetic interactions. Light itself is electromagnetic radiation. Most of the forces you experience daily, from friction to the solidity of matter, emerge from electromagnetic interactions at the atomic level. Gravity moves planets, but electromagnetism moves you. Franklin proved that the fire from heaven follows natural law. His intellectual descendants proved that natural law governs everything. There's no supernatural realm where different rules apply. The universe operates according to discoverable principles, from the smallest quantum fluctuations to the largest cosmic structures. This insight, more than any specific technology, represents humanity's greatest achievement. We've journeyed from cowering before lightning to commanding electrons, from darkness to illumination, from mystery to mathematics. The path from Franklin's hemp string to quantum computers shows what disciplined inquiry can achieve. Every technology we've built, every application we've developed, every question we've answered rests on the foundation of natural law that Franklin helped establish. Yet, the deepest mysteries remain. Consciousness emerges from electrical patterns in neurons through mechanisms we don't understand. Quantum mechanics describes electrons with mathematical precision, but offers no intuitive picture of their true nature. The electromagnetic force has the strength it does for reasons physics cannot explain. We've mastered electricity's practical applications, while its fundamental nature stays mysterious. Perhaps that's appropriate. Franklin didn't fly his kite because he understood everything about electricity. He flew it because he understood enough to ask better questions. Each answer leads to new questions. Each mystery solved reveals deeper mysteries. The journey from ignorance to understanding never ends. It only transforms. The lightning still flashes. The electrons still flow. The global electric circuit maintains its ancient rhythm. And we, Franklin's descendants, continue exploring the invisible force that powers our world and shapes our lives. The kite string connecting us to those Philadelphia storm clouds remains unbroken. We still seek answers in lightning's flash. The story of electricity isn't finished. It never will be. Every day brings new applications, new understanding, new questions, from bioelectricity to quantum computing. From fusion reactors to space-based power, we continue Franklin's work. We stand on his shoulders, reaching toward mysteries he couldn't imagine, guided by the same curiosity that drove him into that storm. That spark between key and knuckle changed everything. It announced that nature's secrets could be discovered, that divine mysteries were natural phenomena, that human minds could comprehend the universe. This lesson echoes across centuries, empowering every scientist, every engineer, every curious mind, asking why and how and what if. Lightning's eternal dance continues. And we dance with it, partners now rather than victims, students of the force that shapes atoms and stars and everything between. Franklin reached up and touched the fire from heaven. We've been reaching higher ever since.